Hello, everyone. Welcome to today's Quantum Spacetime seminar. We are very happy to have Sruthi Narayanan from Harvard, who would be telling us about celestial W1 plus infinity algebra and self-dual gravity. Over to you, Sruthi.
Okay, thank you. I'm happy to be here. I'm excited to tell you guys about some of the stuff that we've been working on over the past year. So I should say that I'm going to be talking about a paper that we put out last November, but it's sort of in conjunction with so many other things that were being done over the course of last year. So I'm going to try to give you a background on some of the results from the past year that sort of led up to this work that we did, just so that it's sort of a more coherent picture for all of you. Okay, right. So I'm going to start with an outline to sort of view a map for all the things that I'm going to talk about, and then I'll go into a little more detail about what all of these things are. So the first thing that we start with is this older idea by Bondi, Metzner, and Sachs in the 1960s, which is that we want to understand the symmetries of asymptotically flat spacetimes, okay? And originally it was thought that, well, maybe the Poincare symmetries were the ones that, you know, characterized everything that we saw, but it turns out that actually we have to consider these soft symmetries in addition to the Poincare symmetries. So in order to understand that better, in the past decade or so, there's been this program dubbed celestial holography, which allows us to recast four-dimensional S-matrix elements, so scattering amplitudes that we calculate in quantum field theory, as two-dimensional conformal correlators in what we call as a boundary celestial CFT. Okay, so there's some two-dimensional theory that's dual to what we would like to consider as four-dimensional quantum gravity. And the hope is that using what we know about two-dimensional conformal field theory will help us learn more about what we expect to see in a bulk theory of 4D quantum gravity. Oh, sorry, that was the wrong order. All right. I will show you all of the things that I have because something didn't get animated the right way. Okay, there we go. So soft theorems coming from these soft symmetries relate an amplitude in momentum space with one soft particle or more than one soft particle to an amplitude without the soft particles. Okay, so that's sort of the basis that we start with to understand what these soft symmetries are. And so we can use what we know from celestial holography to recast these soft theorems as insertions of two-dimensional conformally soft operators. And I will explain to you what those are and how we construct them and what they mean. But what we're allowed to get is what we call conformally soft theorems in celestial CFT. So now what we can do is we have these operators in CCFT, whether or not they're conformally soft, we can construct their operator product expansions. And it turns out that the operator product expansions are obtained from collinear limits of the momentum space amplitudes, which it shouldn't be surprising. You know, we're taking two momenta to be parallel to each other. That should correspond to two operators probably coming close to each other. But if you do the math, you realize that that's actually the correspondence that you see. So once you have these operator product expansions, you can use these, the construction of the conformally soft operators. You can calculate the OPEs of these conformally soft operators. And mode expanding these gives you a series of currents on the in the CCFT. And so you can then do some contour integration appropriately and find what the commutators of these currents are. So basically the commutators of the modes of these soft operators can be obtained from the OPE. Once you have that, the insight of Andy last year was that if you transform these currents via what we now understand to be a version of what's called the light transform, makes the algebra of these currents noticeable as a w-algebra. And so what comes next is, in my head, at least 2 questions, but there are so many more that people are trying to answer right now. But in particular, one could ask the question, since we did everything at tree level, can we add, so we were considering minimally coupled gravity in the bulk. So if we consider additional terms that could appear in a bulk space-time Lagrangian, could we get deformations to this algebra at tree level? Another question to ask is, assuming we have a minimally coupled theory, can we look at the quantum level? So can we look at loop amplitudes in the bulk and figure out if there are corrections to this algebra? Both of these are very important questions. We tried to tackle the second one, so that's what I'm going to sort of end this talk with, explain to you how we did that. But before that, let me move on and sort of give you some more of the details of each of the parts of the story. Also, please stop me at any time if you have questions.
Sorry, would corrections to the algebra translate into corrections to soft theorems?
Yeah, so good. So the algebra, you can derive a couple of ways, actually. So you can, actually, I should say you can get the algebra comes from the OPE, and the OPE can be constructed in a couple of ways. One way is via collinear limits, but the other way is actually by restrictions governed by what symmetries it should obey. So one would expect that if you have corrections to the OP, they should correspond to some sort of correction to the soft theorem also. So yeah, so in particular, one thing we did look at a little bit was loop level corrections to the soft theorems in gravity. But one of the caveats that I'll discuss a little more in detail later, hopefully, is when you look at the soft symmetries, the correspondence between momentum space soft theorems and conformally soft theorems is sort of only known at leading and in some cases subleading order. So it's a little hard to make definitive statements about all the levels of this algebra, or rather all of the currents in this algebra, since they correspond to all orders of the soft theorem. Does that answer your question?
Yeah, yes, thank you. And just to follow up, if you had these classical deformations that you were talking about, you change your Lagrangian, your classical Lagrangian, and you change your algebra a little bit, would that mean that there were classical deformations to soft theorems? And somehow do we know that that doesn't happen?
Yeah, so that's also a good point. So yes, I think the expectation would be that you would have classical deformations, and I'm still sort of wrapping my head around the implications of adding these bulk terms in Lagrangian and how it changes the algebra. But the way I understand it is that it could be one way to sort of restrict what additional terms we could see, what sort of interactions we could have, because we should be able to say, well, we wouldn't expect these sort of classical deformations to the algebra, but we might be able to expect these sort of classical corrections and somehow use that to constrain what sort of theory we want to look at.
Thank you.
Okay, so just a brief primer on celestial holography for anybody who isn't already familiar with it. So the nice part about looking at the celestial sphere is that 4-dimensional Lorentz symmetries that you have in the bulk manifest themselves as 2D conformal symmetries on the boundary. And that's sort of the major insight of celestial holography. It puts this, it gives you a beautiful way to sort of talk about things in 4D in terms of a 2D CFT. And as I said before, we can take 4-dimensional S matrix elements and we can holographically recast them as correlation functions in the celestial CFT that lives on the boundary of this sphere. Operators in the CCFT correspond to some bulk fields that propagate from the middle of space-time out to null infinity, and they're labeled by point Z and Z bar on the celestial sphere. And I will give you a little bit more of the math for how that all works out with the momentum and all that stuff. But as I said, the basic idea here is that whatever symmetries we have in asymptotically flat spacetime, they should manifest themselves as some symmetries on the celestial sphere, and we should be able to understand those in the context of 2D CFT. So how exactly do we do this? What's the math behind this? We want to transform 4D fields to 2D operators. And for massless particles, which is what I'm primarily concerned with in this talk, this is done via a Mellin transform. So I have a field phi of Q, which is just some bulk quantum field, and its energy is omega, and I do a Mellin transform in the energy, and I get some operator on the celestial sphere that's denoted by a conformal dimension delta, and a point on the celestial sphere is z and z bar. The momentum q mu is parametrized in terms of omega z and z bar, as shown on the side. So if I have some momentum space amplitude, which I'll denote in this talk as A of qi, where qi are the momenta of all my particles, then I can transform it by, assuming everything is massless, I can transform it by a series of Mellin transforms. And what that gives me is what's sometimes referred to as a celestial amplitude, but in the conformal field theory is just a correlation function of these n operators that I've transformed. So here I've denoted a operator in the CCFT by this fancy O, but what follows will denote a operator corresponding to a graviton as G delta. So anytime you see a G delta, we're talking about a graviton. Okay, before I continue, it's useful to talk about the signature that we're in, because that plays an important part in this discussion. So another important insight from the past year was, everything so far was done in Minkowski's signature, so 3 space 1 time. But it turns out that actually the better way to understand a lot of this is to be talking about Klein space, which is 2-2 signature. And the subtlety with Klein space is that instead of talking about a boundary 2-dimensional sphere, we're actually talking about a boundary 2-dimensional torus. And there's a beautiful paper from last year by Atanasov, Ball, and others, where they explain exactly what the torus is and how we talk about the Penrose diagram of Klein space, and it's very interesting stuff. But it seems like what we should be doing is starting in 2-2 space. So at the level of the math that I showed you on the previous slide, what that means is we write down the momenta slightly differently. But the more important part here is actually that in Minkowski space, z and z bar, the coordinates that we talk about on the celestial sphere, are complex conjugates of one another, whereas in Klein space, z and z bar are independent real coordinates. And what that allows us to do is, and what will be useful for what I'll talk about in a little bit, is we will need to take limits on the celestial sphere. And in particular, in Minkowski space, there's no way to take a separate Zij going to 0 or Z bar Ij going to 0 limit, so a separate holomorphic or anti-holomorphic limit. You have to take them both together because they're complex conjugates of one another. But in Klein space, you're actually able to take them to 0 independently. And what that allows us to do is it allows us to write down what the OPE is, and 2-2 signature will also be important because it's required for self-dual gravity and among other things that I'll also discuss. So it should be noted that whereas most of the math that has been done in the past doesn't actually rely too much on 3-1 versus 2-2 signature, the geometry of the space that we're talking about does actually depend on that.
One question, Shruti.
Yep.
The ZZ bar in the Klein space, you say independent coordinates, but are they also real independent coordinates?
Yes, they're real independent coordinates.
Okay.
Yeah.
Sorry, one other question, probably very simple. If you looked at your amplitude as a function of z and omega, then there would be a delta function, a momentum conserving delta function that would tell you that it was a slightly singular amplitude. that it would click only when one relation was obeyed.
Yes.
What happens to that? Do you see any signature of the delta function after Mellon transforming?
So
It's
once you Mellon
yeah, sorry.
So yeah, there's a couple ways to Mellon transform. So yes, okay, the amplitude that you have has a momentum conserving delta function. When you Mellon transform, then usually what ends up happening is you use a certain number of those. You can use some of those delta functions in the Mellon transform. And so what happens is in the case of, I think, like if you're talking about an amplitude with 4 or more particles, then usually all of your delta functions get used up in your, in the complete Mellon transform, and they actually don't end up appearing in your celestial.
Your final answer will be a function of only two things. If you're doing 4-particle scattering, would it be like a function of S and T, so that automatically incorporates the momentum conservation in it?
Yeah.
Okay, fine. Thank you.
That's right. Yeah, absolutely.
So,
right.
Sorry, just one question. I mean, wasn't that there this other constraint that your particles need to be coplanar in particular? So you have that this 4-point function would be supported only on some slice in the cross ratio
so that's
space.
Right. So
that's also a consequence of momentum conservation, right?
Yes. So when you do the 4-particle momentum conservation, what you end up getting is actually one of the delta functions is like what you usually see as like the conformal cross ratio of the ZIJs. So there is a restriction there. If I remember correctly, I don't think it was a restriction for them to be collinear. I think in the if you're transforming the 3-point function, then usually there you get like you have to either assume that Zij is non-zero or Z bar ij is non-zero. But I think for the 4-point function, if I'm remembering correctly, then that's not there. But there is a delta function in this conformal cross ratio that comes from
if I might add, so that delta function tells you that the cross ratio has to be real, right?
Yes, right. Exactly. Yeah. Okay. So right. So now we can talk about operator product expansions, which is something that we enjoy talking about in conformal field theory. And the basic thing that we need to know is that if we take 2 null momenta, Q1 and Q2, then in terms of this, in terms of Z and Z bar, their dot product looks like Z12 square. And in momentum space, the collinear limit is when Q1.Q2 goes to 0. So we take 2 particles to be parallel to one another. And as I mentioned before, in Klein space, what this means is we can take either Z12 or Z bar 12 to 0. And so in what follows, usually we take the holomorphic limit. So we take Z12 to 0. So, all of the poles that appear will be accordingly. So the basic thing that you do here is you take the collinear limit in momentum space, and your amplitude should factor in terms of this what we call a splitting function S, which is in terms of Q1 and Q2, and multiplied by an amplitude that's in terms of now instead of n particles, n-1. The subscript there should be n-1 on the right hand side of that equation. And usually you parameterize it by a momentum P, which is the sum of the 2 momenta that you've taken to be collinear. And then what you can do is you can Mellon transform both sides. And if you Mellon transform both sides, then, Z12 is Z1 minus Z2. Sorry, I should have said that. Yeah. So Z12 is Z1 minus Z2, Z bar 12 is Z bar 1 minus Z bar 2. So upon performing a Mellin transform of both sides, well, you can, it's a really nice calculation if you haven't gone through it. It involves changing some parameters around, and you get this beta function, which is pretty beautiful. And basically these splitting functions S are what give rise to this OPE coefficient in terms of the beta function. And as I said before, and it's in this paper by Pate, Reclario, Strumminger, and Yuan from 2019, you can also constrain what this OPE can be, or OPE should be, via symmetries. So you can sort of say, well, the symmetries have how they act on the, or how they act on the fields and how that should affect the OPE, and then you can actually get this beta function via a recursion relation. So in that paper, they showed it both ways. In what we did, we cared more about the collinear, and I'll explain that also in a little more detail, but it has to do with this, how much we know exactly about soft versus conformally soft. Okay, so in this way, you can obtain the operator product expansions. And I should also say that in what follows and what we did, we considered gravitons, but there's a similar story here for gluons. So all of what is done here, you can do for the gluon amplitudes also. But this w-algebra structure is just a little more interesting in the context of gravitons. So
this function, the function S that you've written down, would be, in traditional scattering calculations, would be computed by summing Feynman diagrams? Would it get contributions from all orders in perturbation theory? Or would it? Yeah, good. So that's actually the basis of what we did at loop level. So if you just start, if you consider only the tree level amplitude, which was what was done in this paper, then you're just going to get what the splitting function is at tree level. But in general, you can, if you take the full amplitude, then you should get contributions to the splitting function from every order in perturbation theory. And that actually ended up being exactly what we tried to figure out, whether at loop level there were corrections to the splitting function, which would give rise to corrections in the OPE and therefore corrections in the algebra. So yeah, you in general would expect that there would be terms at all orders in perturbation theory. And this B that you have is just some sort of transform of this S. Is that right? Yeah. So this, when you actually go through the, calculating what the splitting function is, you have to, parameterize these momenta in a certain way so that you can appropriately take the limit. And when you do the Mellin transform of both sides, you end up getting an integral that is just a beta function. So that's, yeah, but again, if you do it via the method of constraining the form via symmetries, then you also get that the coefficients have to satisfy a recursion relation, which tells you it should be a beta function also. So it comes from both sides. And the people who study Feynman diagrams, do they know the structure of S to all orders in perturbation theory, or only to a few orders?
I think they only know it to a few orders. So as far as I know, at least in the graviton case, it's something that's been calculated to a certain number of orders. It's not, I don't know of a full expression that's out there, but that's not to say that there isn't one.
Thank you.
And how does one understand this Z12 bar divided by Z12 factor?
Yeah, so we're looking. Equation. Yeah, so we're looking here at so poles in Z12, right? So that's why the OPE here. Okay, also I should say, sorry, one more comment. This is the leading order OPE. There are, many other terms here in other orders in Z12. So this is, I've just written here the leading order OPE, but in general, there's, a sum over all of the descendants. So this is just the leading pole in Z12, because that's the limit we've taken here.
I mean, this is for some particular operators. Oh, sorry, G delta, you said I should think always of graviton. Okay.
Yeah, this is specifically, right. So this was found by starting with a tree level MHV graviton amplitude. and just, you know, figuring out what the splitting function of that was and Mellin transform expression. Yeah. Okay, so this beta function is worth concentrating on for a minute. Recall that the beta function looks like this ratio of gamma functions. And when the argument of a gamma function is 0 or a negative integer, we have an infinite sequence of poles in this OPE from the beta function. And those are actually of interest to us because those integer weights, right, since delta 1 and delta 2 correspond to the weights of the graviton the two gravitons that we're taking the OPE of, correspond to the soft operators. So these integer deltas, and in particular a certain set of integer deltas, are the ones that give us the soft operators. And that was an important result because when all of this celestial holography stuff first started, the idea was that the basis we should be thinking of in the celestial CFT was conformal primaries that have dimension 1 plus I lambda, so are on this what's called the principal series. But it turns out that actually the more I think at this point what is thought to be the more correct basis to think of, and the in fact potentially the complete basis, although the conclusion of that is yet to be determined, is actually the basis of all of these operators with integer weights. So it's not actually things in the principal series, it's actually all of these tower of soft things. And that's somehow with the picture of, you know, the OPE of these soft things and now the w-algebra, as well as, you know, some of the results that have come out about conformal block expansions, all seems to sort of fit together much better than our original idea of this principal series. So this integer weight poles fact is sort of the crux of why we want to talk about, you know, soft operators and their OPEs and their algebra. So let's now turn our heads to soft theorems. Okay, so as a brief review of energetically soft theorems in momentum space, we know that soft theorems are usually of the form: I take some amplitude which has n+1 particles, one of them is taken to be soft, omega is taken to be 0, and I can now write down an expansion on the other side in terms of in all orders in omega, and each order is, you know, the leading, subleading, etc. soft theorem. And in gravity, the first term goes like 1 over omega, and so usually, so I put this here because I don't know exactly, you know, which literature everybody's familiar with, but sometimes the leading soft graviton theorem is also written where you put an omega on the left hand side so that your soft factor is actually independent of omega. Sometimes the soft factor contains omega. There's sort of different ways of writing it, but you know, they're all saying the same thing. And the important part of these soft theorems, which was this insight from a long time ago, is that every order in here corresponds to some conservation law. So in particular for gravitons, you have your the leading soft theorem corresponds to conservation of supertranslation charge. The corresponds to conservation of superrotation charge, and you know, there should be some tower of conservation laws, but you know exactly what symmetry each of those corresponds to is what I understand to be still an open question to understand. Okay, but what we can do is we would like to think about these as soft theorems on the celestial sphere. And in order to do that, we have to understand what conformally soft means. And the Mellin transform, we know, is an integral over energy. And it switches energy for this conformal dimension delta. So just like your energetically soft theorem is a limit in omega going to 0, you would expect that your conformally soft theorem would have something to do with some limit in delta. And in particular, it was found that the leading soft graviton theorem is a limit where delta star, which is the operator you're taking to be conformally soft, limit where delta star goes to 1. And this factor of delta star minus 1 on the left-hand side is kind of like putting your omega on the left-hand side of your energetically soft theorem. It makes your soft, so the conformally soft factor that appears on the right-hand side ends up being independent of delta star. And this is worth spending a minute or two on, because the you would expect that at every order, just like we have, leading, subleading, sub-subleading, etc., soft theorems in momentum space, you would expect that there is an associated conformally soft theorem at every order. But it turns out there's, from what I can tell, there's a little bit of a conflict in some of the literature about whether we completely understand that or whether we don't completely understand that yet. In principle, you could, one thought is that, all you need to do is take a limit on the left-hand side of this celestial amplitude as the delta goes to one of the integers, and then, take appropriate residues of each side to get what the leading, subleading, sub-subleading conformally soft factors are. But there's a little bit of, it's a little tricky to figure out exactly how you take the residues on either side. The structure is a little complicated. So in principle, there is an associated conformally soft theorem for every energetically soft theorem. Exactly how we write down that correspondence is a little bit unclear. But we do know at leading order, and I think it's subleading order for graviton that's also been shown. And that's all we were working with here. But early last year, there was this paper by Guevara, Himich, Pate, and Strominger, where what they did was defined soft operators. Okay, so soft operators are these HKs, and they're defined as the limit as epsilon goes to 0 of your soft graviton when it has dimension k plus epsilon, where k is some integer 2, 1, 0, minus 1. And the important part about these k's are actually, if you look at the OPE of the gravitons, 1, 0, minus 1, etc., were the poles of this OPE. So we define these conformally soft operators, and that allows us to write down the leading soft theorem as the insertion of one of these conformally soft operators. And so if I insert H1, then I get the leading conformally soft theorem, which, as I said, generates super translations. And if I plug in H0, I should get the subleading. If I plug in H minus 1, I should get the sub-subleading. So this is one way to understand what this tower of conformally soft theorems is.
Sorry, in the last equation, is there a contour integral over Z being done? Or it's just that? And the right
No, there's no contour integral here. So this S tilde is explicitly in terms of Z and Z bar.
Okay.
Yeah, so this is just like how in your energetically soft theorems, your soft factor is in terms of the momenta that you took to be soft.
I see.
Right? Yeah, so it's the same. It's the same thing. In fact, the nice part about the leading soft graviton theorem is that if you just take the energetically soft factor and plug in the momenta, then you get what the conformally soft factor is. But it would be nice to know if that happens at every level, but I'm not sure. But yes, there's no contour integral. Yeah.
These soft operators, they also seem representation theoretically, they seem special in the sense that they seem to be short multiplets of conformal symmetry, right? If you take the usual norm, is that fact useful or relevant at all?
Yeah, so the representation theory of these HKs is sort of the basis for this algebra that you write down. But what you said, what multiplets?
Short multiplets. I mean, it has some conservation type equations.
Yeah.
The primaries obey some conservation like equations.
Yeah. So each of these, so the insertion of each of these corresponds to a word identity in a two-dimensional word identity. So yeah, the insertion of each of these is a conservation law in 2D CFT.
Okay. Yeah. Thank you.
Shruti, I have a question. So if from the bulk theory, we know that once we go to sub-leading or orders beyond that, then there are some non-universal terms in the soft limit, right? Or even the partial, like the factorization is also not complete. There is a part of the amplitude which doesn't factorize. So how does it translate into this celestial picture?
Yeah, that's part of why I say we don't completely understand what happens past, at least I don't completely understand what happens past subleading order for gravity. And I want to say that this this issue with how exactly to take the residue of each side corresponds to these non-universal terms that appear, because we're not sure exactly how one deals with those in that prescription. So I don't really have a good answer for you for what happens beyond subleading level to the conformally soft graviton theorem.
Okay, thank you.
But it's definitely something that we would like to understand, and it should fit into this picture of the sub-subleading soft graviton theorem should in the conformally soft picture correspond to an insertion of H-1. So that's sort of a hint for how we would expect it to be related, but the exact transformation from an energetically soft theorem to conformally soft at that order is a little tricky. Does that answer your question?
Yes, thank you.
Okay. Right. So we've gone from energetically soft to conformally soft. All right. So now we get sort of one of the main results that we started with. And if we start with all of these soft operators, right, these HKs, then any operator in a 2D CFT, you expect to admit a mode expansion in Z and Z bar. So we can write down the mode expansion of HK in terms of, and here we've just written the Z bar mode expansion. So the modes here are actually in terms of Z. And if we take contour integrals of both sides in Z bar, then we can get the modes H and K from the HKs. And here this mode expansion is actually truncated, right? It only goes from K minus 2 over 2 to 2 minus K over 2. And the reason is because, so one explanation for that is that if I actually look at these modes and I look at the norm of these modes, then the norm vanishes for all but finitely many of them. But actually what it is an indication of why what we end up getting in the case of the w-algebra is a wedge algebra. So I'll talk about that on the next slide. But in particular, if you consider k equals 1, which we said generated the leading soft graviton theorem, then you have 4 modes, right? So they correspond to n being plus a half, plus minus 1/2. Then these generate the 4 global translations. So each of
One
these.
question, Shruti.
Yes.
Is there a reason to expect the right norm to take is the one that you're taking? Are there other options? Or?
So the norm that we consider here is an SO2 plus 2 invariant norm. It's possible that there is another norm that you could take that is also valid.
So this seems like the usual norm, right? So if I think of this as some conformal kind of 2D conformal symmetry, then I guess the usual norm that L1 is conjugate to L minus 1.
Exactly. Yes.
Okay.
Yeah.
But is there a okay, fine. I mean, is there a physical reason to expect that that's the right norm?
A physical reason. I don't have a good physical reason for why that's the norm we should consider.
Okay, because because I mean the principal principal unitary series that one talks about, that is unitary with respect to some other norm, right? So that's why I'm asking that now you kind of switch the norm and obtain these nice representations.
Exactly. So yeah, so the previously we were trying to understand if one considered the principal unitary series, what was the best norm to consider there. But now that we've sort of moved to Klein space, we're talking about, there's I don't have a good answer for you for why this is the norm we should be considering. And honestly, it is entirely possible that there is a better one. But
okay, thank you.
Unfortunately I don't have anything better for you in that aspect. Right, so as I said before, now what I can do is I can take the OP of the two. Yes.
Maybe this makes no sense, but I was wondering if one studied unitarity of the S matrix, one would have to introduce a complete set of states.
Correct.
And that would give you a natural norm then, right?
Yes.
So perhaps Abhijit's question is whether it could be rephrased. I'm not sure, but perhaps it could be rephrased as whether this is the norm that is appropriate for
right, unitarity of this matrix.
Yeah. And so as I said, I think there's some current work being done, so hopefully we'll see it soon, but about the completeness of this set of operators with integer weight. But I should say that one thing that's a little funky is that if we're talking about 2-2 signature, we don't actually have an S matrix. We have what's called an S vector. So I think there's still something to be understood about exactly what we are talking about when we talk about an S matrix and 2-2 signature. At this point, I think we've just sort of been taking it for granted a little bit, that we should be able to transform on the celestial sphere in this way and all that sort of stuff. But yes, this question of unitarity of the S matrix and how that fits into a complete basis on the celestial sphere has been a question that we've been trying to answer for a very long time. So and hopefully looking at whether these operators form a complete basis in the CCFT is one step in that direction.
Okay. And sorry, since you brought this up, this 2,2 signature, at the moment I'm thinking of an analytic continuation of 3,1. I'm not thinking. Yeah. So it's just some mathematics, right? We should give it no physical reality.
Yeah. So okay, good. So that's one way you could. Yes, that's one way you could think about it. And I think in this, there was a recent paper by Crawley, Miller, Guevara, and Strominger also, where they talk about black holes in Klein space, and they do talk more explicitly about how, you know, transforming to Klein space is just an analytic continuation of one of the coordinates. So yeah, and you can see it also from the way that we define the momenta. It's just a question of multiplying something by I. Yeah, and so I think the preferred thought there is that that's the way that it should work out in the end, that it's just an analytic continuation, it's just some math that we need to do, and it doesn't actually affect most of, you know, the physics that we're talking about, except for maybe the fact that like the geometry on this space is a torus. But yeah, that's also something that's being actively discussed, and you know, there's a lot of new thoughts in that direction. So
thank you.
Yeah. Right. So as I said, we can generate these modes by taking contour integrals of these soft operators. So if I start with the OPE of two soft operators, then I can contour integrate both sides, and I can figure out what the commutator of these modes are. And as you can see by this complicated expression at the bottom of the slide, this is not a very easy calculation. So if you're interested in exactly how it was done and all of the caveats with taking the contour integrals and all that sort of stuff, it's in the paper from last year. But the point of this is that you get kind of a complicated algebra of these modes, and it's a little bit unclear exactly how to understand what that algebra is. And
so what is happening
so finally, sorry?
What happened to the Z dependence?
Sorry. All of these modes that I've written here are in terms of Z. So we've taken contour integrals over Z bar, but these HK, HL, and HK plus L are all in terms of Z.
Okay.
So
yeah, okay. I mean, usually we talk about holomorphic guys and take their modes. I mean, and then that forms the algebra, right? Here.
Yes.
Yeah. Okay.
Yeah. So what I mean, you can talk
here,
about
in some sense, there is three labels, right? There is your delta, there is a K label, and then there is an N label, and if you mode expand in Z further, then you get another label.
There will be a third label, right? So this is what's, you know, usually done if you want to figure out, you know, the commutators between, you know, like the LNs or something like that from the tensor, etc. Right. So usually you have two, and I mean, you can do that too, but I think this was more to see, you know, these so these modes HK that are in terms of Z are actually should be thought of as currents on the celestial sphere. Yeah. And so when you actually take contour integrals of insertions of those currents, then you end up getting the associated conservation laws. So these are, you know, that's how you actually generate all of these word identities, which is why it makes sense to have them as you know, things in terms of Z rather than completely mode expanding in terms of Z and Z bar.
These contour integrals are taken only in Z bar, not in Z?
To get this algebra here, yeah, these are just contour integrals in Z bar. Okay. Right. So this is purely just to extract the modes from this expression at the top of the slide.
Sorry, Shruti, can you repeat what will generate your symmetries?
Yeah. So if you insert these HNKs, right? So the modes of the HKs, and then if you perform, so those should be thought of as currents that generate a symmetry. So if you insert those into your correlator and then you take a contour integral over Z, then you should be able to generate the word identities of your two-dimensional word identities on the celestial sphere.
Okay, but from the bulk perspective, HK corresponds to a single symmetry, right?
Correct. So HK corresponds to a single, so it corresponds to the leading soft graviton theorem, right? So it corresponds to a single symmetry, but these modes that you write down in for example, H1, right? H1 here has 4 modes. And those modes actually generate these 4 global translations. This is also written, I think, if you want the details of exactly how this works, it's also written in this paper from last year. They do a little more of a general discussion. But for our intents and purposes, what we cared more about was, you know, the algebra of these HKs.
All right, can I ask a question as well?
Yeah.
So this commutator on the left-hand side, the 2 HKs, HK and HL, are evaluated at the same point Z?
Yeah, so here they should.
In that case, is it clear that there's no singularity? If you evaluate them at different Zs, then you take the limit that Z, one Z approaches the other Z. Is it clear that there wouldn't be any singularities? Is it possible?
No, there's absolutely a singularity. So right. So the commutator, well, I guess
well defined, in other words.
So there's if you take the OPE of these 2 HKs, then you find that there's a pole in Z12 where one of them is taken at Z1 and the other one is taken at Z2. In the actual commutator of these modes, you don't find that. So in the commutator, what you should think of is that both of these are taken to be at Z. And so on the other side, this HK plus L, M plus N is also in terms of Z.
Okay, so basically it's already normal ordered in a sense. I mean, you
Correct.
think
It's
of the whole
already normal
commutator
ordered.
inside normal ordering.
Right.
I
Right.
see. Thank you.
Yeah. Okay. So, right. So as I said, that algebra that they obtained for these modes HK was pretty complicated. It had all of, you know, there's a lot of factorials, etc. But in this paper by Andy last year, he realized that if you write down a redefinition of these modes, so write the HKs in terms of these W's, then there's this algebra actually looks very simple. And this algebra is something that is has been present in some of the literature from before, and it's a W1 plus infinity algebra. And it's so in most of the literature right now on this stuff from the past sort of 6 months or so, it's referred to as the W1 plus infinity algebra. But because you actually have this restriction of the modes, right? We had this range, you know, this range in this HNs here corresponds to also a similar restriction in the range of the omegas that you consider, or the range of the W's that you consider in this algebra. And so that it's actually a wedge subalgebra of the full W1 plus infinity algebra. So this is kind of like how, you know, you have that SL2C is a wedge subalgebra of the full Virasoro. But this was sort of this is a very interesting conclusion, because now we have an algebra of these currents on the celestial sphere that, you know, are related to the symmetries that we expect in our bulk theory. And so the natural question to ask here is, can we use this algebra in the boundary to figure out what theory we should have in the bulk? Okay, so this is sort of the guiding question that I think a lot of people in our group and you know, tangential groups are sort of operating under right now is, can we use this to understand what theory we might have in the bulk? In particular, in the past, long time ago, this algebra appeared in Penrose's twister construction, and there's a big group of people now working on how to understand this from the twister viewpoint. I don't personally claim to understand all of that literature very well, so if you are interested in exactly how that how that appears in this context, I would direct you to papers by this group at Oxford, Adamo, Mason, Sharma, and others. They have some very good papers on this sort of stuff. But also it appeared in studies of W1 plus infinity gravity, which were theories that had a boundary symmetry W1 plus infinity. It's also appeared in the context of the C=1 string. So it's possible there's some implications there for how this relates to string theory. That would also be interesting. But the point is, now that we know that this is a W1 plus infinity algebra, we have sort of some very big questions that we can ask here.
Sorry, Shruti, you said something that confused me. You said that you're to try to use the structure to constrain the bulk. What I thought you were doing so far was to take what you get from the bulk and translating it to the boundary.
So we're assuming that we have we're assuming some basic things about the theory that we have in the bulk. We're assuming that we have an asymptotically flat space-time that has some, so our theory of quantum gravity is in some asymptotically flat space-time. And because it's an asymptotically flat space-time, it should have some set of symmetries, right? Which are all of these soft symmetries. And we've translated those soft symmetries to symmetries on the boundary. But now what we're hoping is that because that the algebra of those generators is w-algebra, understanding more about why this w-algebra could arise could give some indication of, more, or could give more insight into what you might expect in the bulk. So one shouldn't think of it as like constraining. Sorry, maybe that was the wrong word. One shouldn't think of it as constraining what the bulk theory is. More of sort of, we have now an additional tool that we can use that has been understood to some degree before that might give us a little more insight into what we would expect.
Yeah, I was wondering if, if somebody added a new term to the bulk Lagrangian, let's say a Riemann to the 4th term.
Sure.
Could it, was your hope that new term would spoil some of the structure and therefore be sort of illegal, or?
Yeah, so good. So so since you said that a couple of times, I should mention that there's a very recent paper by Anastasia Volovich and others from Brown where they do the calculation of exactly what term, if I add certain terms in a bulk Lagrangian, how does it change the algebra on the boundary? So they do actually explicitly figure that out. And yes, so I think the goal would be to make some sort of conclusion about this has changed my algebra this much. Should I be throwing out such a change because I don't think it should be there, or is that an addition to the algebra that is worth keeping? But I'm not personally very clear on exactly how one would make that conclusion, how you would come to that conclusion. It seems like figuring out how so the difficulty, I think, is that in writing down, for example, the OPEs, right? We have started with MHV amplitudes in the bulk. So we've already sort of assumed that, our amplitudes have a certain structure. So if you want to actually make some constraint or restriction on what you would expect in the bulk, then you need to have, in some sense, a completely general description of what your bulk theory could be, and know exactly all of the boundary terms that could arise from that general description. And then you would be able to say, well, if this term appears in the algebra, it cannot correspond to this general model I've considered, therefore we have to throw it out. And I think that part just sort of isn't there yet, because a lot of what we have done has been, we have to use what we already know about amplitudes in 4D space, and we have to sort of use all the things that we already know to figure out what this stuff is on the bulk. But it's a very interesting question, and I think it's sort of the heart of what we're trying to get at here with all of this. But it's so new at this point that there's a lot there that's yet to be understood.
Thank you.
Shruti, one question. So this is kind of not a very concretely framed question, but algebras I usually think of as very rigid and robust objects, right? Because of Jacobi identity. Now this but the space of Lagrangians is quite rich. I mean, you can add a whole bunch of terms there. So how does the correspondence work? I mean, unless this algebra is not there for certain, for some region of Lagrangians, region of space in the space of Lagrangians. Yeah.
So I think one thing to check is, for example, if I have some additional term that I consider in a bulk Lagrangian, and like Shiraz was saying, then it gives rise to some change in this algebra. Does that affect whether or not it satisfies the Jacobi identity? Right? That seems to be one check one could do to try to figure out whether or not, and maybe if it doesn't, you might be able to say something like it doesn't satisfy, or it breaks the Jacobi identity somehow, therefore this might not be something that we can consider. Again, I'm not okay. Yeah, I that's kind of the best answer I can give for that right now, because even I had not, so I should admit I had not appreciated the importance of this algebra until last week, or rather the week before, when I listened to lots of talks where people were talking about the implications of this algebra, and what happens if we change the Lagrangian this way, and what we might be able to say about what the theory is, and so I'm still early in my understanding of exactly how all of this fits into this big picture of what is the theory in the bulk. So, but yeah, that it's as I said, definitely a very important and very central question to be asking, how we could use the algebra and its structure, and how rigid it is to understand what theory we could have.
So just a vague comment about what Abhijit was saying. It looks like you're looking at these soft theorems to all orders.
Mm-hmm. Yeah.
Now, if you were looking at soft theorems up to some order, then you would imagine that terms with higher than a certain number of derivatives don't contribute, because those derivatives would not contribute very much to soft behavior. But since they're looking sort of like to all orders, it feels a little bit like every term in the Lagrangian will contribute somewhere. Mm-hmm. So maybe there is, because of that, a one-to-one map somehow.
Okay. But the algebras usually are rigid, right? So.
Right. I don't know what to say about that.
Okay.
Sorry, one more.
Actually, Anastasia is on the audience. If she has any comment, it would be nice.
Well, what we did was systematically looked at the corrections to the algebra and made sure that it closes. That's basically all. But the corrections to soft theorems, there was a paper by Henrietta and others looking at that. But we didn't assume any corrections to the soft theorem. So we just literally looked at the corrections to the OPEs and made sure the algebra closes and worked out what the algebra is. So very minimal. Yeah, but we're looking at more cases now. Yeah.
Thank you.
Yeah, that's right. We also looked at that paper by Henrietta and it was another author, but yeah, where they talk about corrections to soft theorems that arise from these non-minimal terms in Lagrangian. So yeah, that might be another way that you could, since the way that we're talking about it here is getting this algebra from the OPE and looking at how these terms change the OPE. Another way would be to try to understand from the soft theorem point of view. If you look at how these interaction terms modify the soft theorems, then you should also be able to figure out using, arguments for how the soft theorems and soft symmetries constrain this, constrain the OPE, how that changes too. But okay, so maybe in the interest of time, even though this is a very interesting discussion, I'll move on so I can get to the main result of our paper, which is coming very soon, I promise. So as I mentioned before, there's a couple questions we could ask, right? So what we've talked about a lot is this second question, right? We assume minimally coupled gravity in the bulk, but what if we have some other interactions, some more exotic things? At tree level, does this algebra get deformed? What happens to it? Does it make sense? Okay, so that was one very clearly very important question that we could ask. But another question to ask is, we're looking at this from tree level MHV. Does it receive corrections at the quantum level? So this was brought up earlier as well. What happens if we consider the amplitudes at loop level in the bulk? Does that arise to corrections in the algebra? And that would have some important implications. Is this a symmetry that's somehow broken at the quantum level? If it's broken, is it maybe could you understand whether it has some sort of associated anomaly? Is it something that is spontaneously broken? Is it or is it not broken at all? And what we found was that considering a fully general theory in which to do this is a little difficult, because if you want to understand whether it receives quantum corrections, then you have to consider all orders over tree level. But if you consider self-dual gravity, then it turns out that this is a very concrete problem, because quantum self-dual gravity actually has a finite set of S matrix elements. So what we did is we answered the question of what happens to this W algebra at the quantum level in self-dual gravity. And self-dual gravity at the classical level is just defined by this condition on the curvature tensor. And in particular, this also goes back to the fact we were talking about 2-2 signature. And if you're not in 2-2 signature, you don't actually have a way to understand self-dual gravity, because you can show that it's just, it's trivial in 3-1 signature. So another reason why it's good to consider 2-2 signature, but maybe oppositely, a good reason to consider the theory of self-dual gravity. Self-dual gravity has also come up in discussions of W algebras in the past. So that was the other motivation for considering this theory. But I should say that when we tried to understand exactly how to write down the S matrix elements, we came across many formulations in the literature. There's many people have written down many different Lagrangians for self-dual gravity with, some people have written them in with Lagrange multipliers, and you need to integrate out the fields to figure out what the equations of motion are. There's some arguments that are, from a string theory perspective, there are, and not all of them are actually in agreement on exactly what the S matrix elements are for self-dual gravity. So we ended up choosing a convention that's in a paper by Chalmers and Siegel from '96, but also in several subsequent papers by Byrne and others, where they talk about amplitudes in self-dual gravity, where the S matrix elements have 1 minus L negative helicity gravitons, where L is the number of loops. So if I'm at tree level where L is 1, that means I just have 1 negative helicity graviton, and the only tree level amplitude we have that's non-trivial is the 3-point plus plus minus amplitude. And so I've used spinor helicity variables here. 1, 2, 2, 3, and 3, 1 are just usual spinor helicity things. But at loop level, what that means is since L is 1, we have no negative helicity gravitons. And in general, the all plus 1 loop amplitude for gravitons was given by this very complicated expression in this other paper by Byrne and others. I won't spend too much time explaining what all of these things are, but this H that appears here is called a half soft function. The way that they constrained this form of the 1 loop amplitude was by using soft theorems. So basically they said that we expect it to obey these soft theorems, and they recursively were able to write down what the endpoint 1 loop amplitude was for all plus gravitons. Again, there's a whole bunch of spinor helicity here. These capital Ks correspond to sums over momenta and all that good stuff. But in this paper that I've referenced here, they actually calculated the splitting function, right? So recall back to what I said about a half hour ago. The splitting function, right, was found by taking the collinear limit of a momentum space amplitude, then Mellin transforming that gave us the OPE. And from the OPE, we were able to take contour integrals and get the algebra. So if we work backwards, we would expect that if we have corrections to the splitting function, they should, or they could propagate as corrections to the OPE, which could propagate to corrections to the algebra. Of course, anything in there could, you know, get canceled out somehow, could disappear at some order, all that sort of stuff. But the first thing to look at is whether the splitting function gets corrections. And in the literature, the splitting function was shown to be the same at loop level. But what they did was they took what we called the true collinear limit, which is where Z and Z bar were taking to 0 together. And what we wanted to do was actually figure out what happens, since we're in 2-2 signature, what happens when we take Z12 to 0 independently and keep Z bar 12 fixed. Okay, so we needed to do something slightly different, and that was sort of the main calculation that we had in this paper was what happens to the splitting function at 1 loop. And of course, okay, I should have said this earlier, but since the S matrix was defined as 1 minus L negative helicity gravitons, once you go to 2 loops, you would need a negative number of negative helicity gravitons. Therefore, there's nothing higher than 1 loop. So that's why this model of quantum self-dual gravity was nice to consider, because it was a very concrete, very you know, small subset of things to consider. So it was a nice toy model. And okay, the more in my view, the more boring aspects of this, we, you know, took this complicated loop amplitude that I have here. We parametrized the momenta to take the collinear limit. And after lots of algebra, we found what the collinear limit of these half soft functions were. And the long story short is that we were able to show that for 1 loop, the splitting function is exactly the same at tree level. So the splitting function remains unchanged. And that was already all we needed to determine that in the model of quantum self-dual gravity, there were no corrections to the W1 plus infinity algebra. So in fact, it's uncorrected, and the symmetry exists to, well, all orders in perturbation theory, since here we only have 1 loop. A kind of interesting mathematical fact, it turns out that when we did this calculation, we found an additional term that was proportional to this ratio of spinor helicity things, which vanishes if you take the true collinear limit, so vanishes if you take both Z12 and Z bar 12 to 0 at the same time. But here it exists, and this was a source of a lot of concern or confusion, because we thought that would actually give us some correction to the algebra, and for a while we were trying to understand what that would mean. But turns out it's proportional to this thing that was shown to be identically 0, which is kind of amazing that that worked out that way. And, you know, it was very exciting for us. But it just goes to show you that there are a lot of interesting math identities like this out there that a lot of people have figured out. So, but yes, so let me just end by walking you through what I talked about here, because it was a lot of stuff. So we talked about how soft operators generate symmetries of asymptotically flat spacetimes on the boundary, so on the celestial sphere. We then showed that OPEs of these operators are found from collinear limits of the bulk amplitudes, and they can also be found by symmetry constraints, but we considered the method by which you use the OPEs. If we contour integrate there, then we can see that their modes form this W1 plus infinity algebra. And we wanted to see what happened at the quantum level. So we considered quantum self-dual gravity, where we had only one tree level amplitude and only all plus amplitudes at loop level. The important way to come to the conclusion is that loop corrections to the algebra will be found from corrections to the OPE that will originally come from corrections to momentum space splitting functions. And since we were able to show that the splitting functions are the same, our conclusion was that in quantum self-dual gravity, this W1 plus infinity, this classical W1 plus infinity algebra remains uncorrected at the quantum level. Of course, I should say that was a toy model that was very nice to consider and could have other implications. I'm not entirely sure, but you know, it does not say anything about what happens if I take a far more general theory in the bulk, and you know, whether that is uncorrected or corrected or anything. So that would definitely be very interesting to see if you considered a more robust theory, what happens to this algebra. Okay, sorry for going over time. The questions are great, but anyway, that was all I had to talk about.
Let's thank Shruti for a very nice talk. If there are questions, please ask.
So, Shruti, can I come back to a question I think Sayali asked at the beginning of the talk about things I don't know well, but she was asking whether, if I understood right, whether if you work to all orders, this splitting form persists that you get.
Yeah.
And that seems sort of important for your talk, since your w-algebra is defined, uses all orders things.
Right.
So does the existence of this w-algebra depend on this splitting form working at all orders?
So, okay. I think the statement at all orders can be a little bit confusing here, right? So the initial discussion starts with a tree level amplitude in the bulk, right? So if I start with a tree level amplitude, sorry, let me take one step back. There are two separate definitions of all orders. You could be talking about all orders in a small omega expansion, right? So that's if I take the soft theorem or soft limit and I look at all orders in the soft limit. Or I could be talking about at all orders in perturbation theory, which is different because, you know, now I'm talking about whether I'm talking about a momentum space tree level amplitude, a loop level amplitude. So this is perturbation theory and whatever coupling I'm talking about.
I was talking about the first thing in a derivative.
Right. Yes. Good. So yes. So our this analysis does rely on the all orders of the soft limit, because all orders of the soft theorem are what give you all of these modes, right, that generate the algebra. But I thought, so maybe I misunderstood Sayali's question. I thought she was asking about the splitting function at all orders in perturbation theory.
Maybe I misunderstood.
Okay. I may have misunderstood too. So I was answering her question assuming she meant the splitting function at all orders in perturbation theory. And this argument does not rely on it, because if you're just considering tree level, then for the OPE, all you care about is the splitting function at tree level.
But suppose I asked you her question for all orders in this derivative expansion.
So
all orders in omega. Is this form always, true? Does that persist to all orders?
Well, I mean, so we could talk about taking, okay, yeah. So this might be an order of limits question. So the OPE, if you don't consider soft gravitons at all, right? If you just consider the OPE, then I start with some tree level amplitude. I take the collinear limit. I get the OPE of two gravitons, right? There's no ambiguity there. Now I can take, usually what's done is now you take the soft limit. So you do this thing where I multiply the operator by epsilon and I take the dimension to an integer. So now I have, so in obtaining the OPE, I have already used the splitting function, right? So I have assumed, I guess, in that order of limits that the splitting function is valid at all soft orders, so all orders in the soft limit. I guess if you, so I don't actually know what happens if you do it the opposite way. So if you decide to take the soft limit first and then figure out what the collinear limit is. And so, okay. I think this is an important distinction, because this is basically the question of whether I should take the soft limit or the collinear limit first, right? Because I'm using both limits here. So it's, do I take two particles to be collinear first and then take the soft and then take them to be soft, or do I take them both to be soft and then take them to be collinear? And in one case, you don't need to ask the question about whether the splitting function is the same at all orders in the soft expansion. But in the other case, you do, because you've taken the soft limit first. And I guess I don't know the answer to whether or not those two orders of limits are exactly the same. But I guess here the assumption is that those two orders of limits are the same.
Thank you. Actually, could I just ask one more about this?
Yeah.
It's probably a very stupid question. If you could go back to the slide where you had the splitting function first, please.
Yes. Yeah.
Right. So what, of course, is at least what to me was sort of striking here is that this S here seemed independent of what else was going on in your amplitude. Right. Then you take two guys together, and then, irrespective of what else is happening.
Yeah.
Now, we're familiar with that being the structure of OPEs in a conformal field theory, but I was wondering whether it was this was always true for scattering amplitudes.
Yeah, so I think you can show, I think there's an argument in Weinberg to this effect, where you can show that but the argument in Weinberg might be at tree level. So you can show that, like, if I write down some endpoint scattering amplitude and I want to take two particles to be collinear, then just by the propagators that appear in that, in the from the Feynman diagrams, you can show that it has to factorize like this. So it has to factorize where you have, it's like a pole in 1 over, I think 1 over P1 dot P2 times something. It has to factor out that way. Not remembering exactly the argument that he uses, but it is there in his quantum field theory book.
Thank you. Thank you.
One more just question.
Yeah.
So could it be that, so in order to get to this W in 1 plus infinity algebra, you had to do this light transform, right? To get to that. So could it be that the effect of this other, the modification to the theory be basically taking you to the algebra, but in some other transform basis? So
what do you mean
in
by
that sense, the algebra itself is unchanged, but you get some, I mean, you got the modes, but they were not, you didn't quite recognize them to be W algebra. So I'm saying there could be some mixing going on as because of the addition of, I mean, the algebra itself might be isomorphic. So, sorry, this is just first, zero thought of thought, but it could be wrong.
Yeah. So, yeah, the fact that these two things are related by a light transform is, I mean, okay, so when it was done at first, we didn't even talk about it in the context of a light transform. It was literally just, we can redefine the operators or redefine the modes. So I can make an, I can just map the modes. So in that sense, yeah, the two algebras should be isomorphic to one another just because they are. So I don't think that the algebra that was originally written down was not a W algebra. I think the statement is that, it just wasn't easily recognizable as one.
Yeah. So what I'm talking about is that when you, I had asked this question of, if you add some more terms to the Lagrangian, then the algebra might get deformed or remain unaffected, etc. I'm saying there is a place for these parameters to appear. It could be the parameters involved in this change of basis. So at the end of the day, the algebra might still be the same, just that it will present itself in a different way. I don't know. This is, I don't.
So the explicit relation using the light transform is also written in one of these recent papers by Himwich and Pate and I think Kyle Singh. So it might, the only reason I hesitate to say whether that could happen is because it looks like there's just, I'm not sure exactly how these other things would appear just via the light transform. It might be possible. It's not. Okay. Yeah. It would require also a little better understanding of the light transform, which I don't actually understand exactly how to interpret a light transformed operator, because it takes, for example, it switches the conformal dimension and the spin. So it's, I'm not entirely sure how to understand what a light transformed operator is. That's something I've been thinking about. But yeah, it is. I wouldn't ignore the possibility that it might be related to exactly how to think about these extra terms. That would definitely be interesting if that happened.
Actually, I have a perhaps related question related to this W1 plus infinity algebra. So if indeed it's the case that this algebra should be thought of it as being inside the normal ordering so that we avoid the infinities, the contact terms, the infinities that we talked about, then it's typically the case that local operators, normal ordered operators, depend on the regularization prescription, the normal ordering prescription. So then one can ask what happens if you change the normal ordering prescription. And because the algebra, so you have a quadratic W on the left-hand side and the linear on the right-hand side, this consistency requirement might be non-trivial, and one might perhaps learn something by requiring that the results are independent of the normal ordering prescription.
Yeah, I hadn't thought too much about that, but that's a good point, because presumably yeah. Okay, I would have to think more about what changing the normal ordering prescription would do to this, would do to the commutator. But yeah, in principle, it would have, it would, if it wasn't invariant under the prescription, then it could have some extra terms, it could have some extra structure that would, be interesting to look at too. So yeah, that's a very interesting thing to look at for sure.
Sorry, one quick question.
Yeah.
For the equation of unitarity on A, N, and Q's is quite clear, right? It's just Kutkowski's rules. Take S and S and you compound it. Now, if you wrote down that equation and then you try to transform that equation into Mellon space, is that a difficult thing to do?
I don't know, because I've never tried. I do.
And nobody's tried this, as far as you know?
As far as I know,
it seems like the natural thing to do, right? Because it's a true equation that will constrain your structures.
Yeah. It's possible somebody has tried it, because, as I said, this question of unitarity has been a long-standing one in celestial CFT. So, but I don't know offhand what the conclusion of that was. But yeah, that's definitely. That's a very natural question to ask if you're thinking about unitarity. So I would be surprised if nobody had attempted to do that. So my guess is there must be something tricky that happens when you try to Mellon transform, but I don't know offhand.
So if there are no further questions, let's thank the speaker again.
Thank you for all your questions. That was
Thank you, Shruthi. Thanks for nice talk.
Yeah.
Thanks, Shruthi. That was absolutely great. It was very clear. Thank you so much.
Yeah, always happy to talk about this stuff. It's yeah.
Thanks a lot.
Bye. Thank you.